So we'll continue this morning's session with Pierre from the University of California at Berkeley, who will talk about finite dimensional omega-categorical structures.
Okay, thank you very much. Thank you for the invitation to speak here. So the result I really want to talk about is something in pure model theory. But since this is a model theory and combinatorics conference, I'm going to focus mainly on a special case and an application of it to the study of NIP omega-categorical structures, or something more subclass of that, really. And this way, so I'll sort of do things in reverse, and this way I have to introduce almost no model theory for most of the talk. Okay, so I'll start by recalling certain things that already appeared, at least in David Evans' talk. So a countable structure is omega-categorical if the automorphism group acts on it oligomorphically, which means that you have finitely many orbits on every Cartesian power, so finitely many orbits of n tuples for each n. I listed a few examples. I'm going to go through them because they'll be useful later on. So M, by this, I just mean the infinite set with no structure, just equality. Okay, that's omega-categorical. Q with the order. This one, by this, I mean circular order. So this is a structure. You take a countable dense subset of the circle, and you have a ternary relation C of x, y, z, which holds if and only if the points x, y, z are in that order, say, if you turn clockwise around the circle. So this is very similar to a linear order, but if you name a point, you get a linear order, but there's no actual linear order definable on it without parameters. The random graph, so I'm assuming most of you know this, is the unique countable homogeneous universal graph. Slightly different are FP vector spaces. So you can see this just as a pure group. This is also omega-categorical. And then trees are also will play some kind of role, a negative role, in this talk. So let me say what I mean by that. So here I'm looking at meat trees, which is just for convenience. So for me, a tree is a partial order such that if you take any point in it, the set below that point is a chain. So that's the definition of a tree. And the meat, this is a binary function, which just, if you give 2 points A and B, then the meat, A meet B, is the greatest upper bound. So we're assuming that it exists. We have such a function in our structure. And it's dense means that, so you take sort of the Freise limit of such things. So every path is a dense linear order, and in over every point you have infinite branching. So that's what I mean by this dense meat tree. And that's also omega-categorical. A special case of omega-categorical structure, which was also already mentioned, are finitely homogeneous structures, which just means they're homogeneous or ultra-homogeneous, if you want, in a finite relational language. So you have a finite relational language, and if two finite substructures are isomorphic, there's an automorphism mapping one to the other. All of the above are such, except for FP vector spaces. So for the dense meat trees, I did put a function symbol, but you can change the language and get rid of the function symbol. For the FP vector space, you can't do that. So there's no finite relational language that makes it homogeneous. So finitely homogeneous structures cannot have a group structure, a definable group structure on them. And so they're, in some sense, purely combinatorial objects. So as far as I understand, the problem of classifying all omega-categorical finitely homogeneous structures seems hopeless. So finitely homogeneous, you have lots of them. And in particular, you have a big class of them that come from generalized metric spaces. So you fix finitely many distances that are allowed, and maybe some constraints, and you take a universal object if it exists. And sometimes this gives an omega-categorical or finitely homogeneous structures. For example, another example is the triangle-free random graph. So instead of, you do the same thing as for the random graph, but you restrict to graphs which have no triangle. So that's also a Freyse class, and you can also have a universal object, universal homogeneous object. But so what's natural is to try to classify subclasses, and since we're model theorists, based on model theoretic properties. And here what I'm interested in is there seems to be, so you have all those structures like random graphs, triangle-free random graphs, which have some randomness. I mean, it's in their name. And so okay, and this is in sharp contrast with things like linear orders and trees. So we can try to classify omega-categorical structures that in some sense exhibit no random-like behavior. So I'm thinking I really have linear order trees, FP vector spaces in mind as being structures which are much more geometric, much more structured. Okay, but for this we need to define this class more precisely. This is not meant to be a precise definition. And so the real definition, I mean the thing that is similar to that in model theory is NIP. I'm not going to look at all NIP because I'll say a few words about it later, but even all stable omega-categorical structures can probably not be classified. So I will look at the following. Okay, so let's make the following definition. So if you have a finite A, you can look at the set of 1 types over A, which, if you're not model theorist, this is just the set of orbits under the pointwise stabilizer of A. Omega-categoricity is exactly telling you that all those sets are finite. You have finitely, if you fix a finite set, you have finitely many orbits. And in particular, if it's finite, you can look at its size. And let's look at examples. So if you take a set with no structure, and if you fix a finite set of size n, then you have n plus 1 orbit. You have the endpoints that you're fixing, and then everything else is just 1 orbit. If you take dense linear orders, if you take n points, then you have 2 n plus 1 orbits. You have the endpoints are each 1 orbit, and then the n plus 1 intervals that they define are n plus 1 orbits. If you take FP vector spaces, if you take, well, the vector space generated by a set of size n has size at most n to the p, and then everything outside is just 1 orbit. So you have big O of n to the p orbits. If you, however, take a random graph, well, if you fix a set of size n in the random graph, again, the points that you're fixing form n singletons orbits. And then you have 2 to the n orbits, because just orbits are determined by whether you have an edge or not, to which points of your finite set you have an edge, and all the 2 to the n possibilities exist. So okay, so what we see is there's a sharp difference. This randomness from the random graph is witnessed sort of by this 2 to the n here, by this exponential growth. And here we have polynomial growth in those structures. Okay, so that's exactly what I'll take as a definition. And just for the purposes of this talk, I'll say that M is finite dimensional if the space of type has polynomial growth. And I call it finite dimensional because it, well, I want to think of it as that, as some kind of finite dimensional structure. But you shouldn't maybe take that too seriously. And the conjecture, hope, which is willingly imprecise, is that finite dimensional omega-categorical structures can be classified or can be understood. And I don't have precise conjectures for this class, but there'll be lots of conjectures in this talk. I'll have conjectures for subclasses. well, I could try, but it's not completely clear what exactly here I mean by classifiable. But those structures should be very, very structured. There shouldn't be too many. You should be able to understand them. All right, so before I state some results and conjectures, I want to step back a little bit and tell you about the history of this kind of problem, in particular the stable case, though I'll be very, okay, I won't go into too much details. So, okay, stable was already defined. I'll just go through it. So a formula is stable if we cannot find, so here I'm working, say, in the omega-categorical. I don't need to worry about saturation or anything. So if you cannot find two infinite sequences of tuples such that the formula precisely orders, so the formula holds of ai bj, if and only if I is less or equal to j. So this is the bad property. This is, so a formula is stable if you cannot find such two infinite sequences. Graph theoretically, this means that the formula sort of defines a half graph on some, well, there's an induced half graph inside defined by the formula. And the structure is stable if all formulas in it are stable. And in the list that I had before, the only stable ones are just pure equality and FP vector spaces. And everything else, well, everything else either had explicit linear orders or just partial order is enough to, so trees and linear orders. And the random graph, it contains every countable graph. So in particular, you can take the edge relation to be phi, and you can certainly find points like this. So it's tempting to want to classify omega-categorical stable structures, and there were a lot of conjectures at the time. And then Hrushovski came up with this construction that David Evans talked about, which supply which give us a large supply of stable omega-categorical structure. And I don't know if there are any conjectures still open, or if there's still any hope of having some kind of classification, but it's at least, I don't think we know how to do that. However, there's a subclass of this that has been very well studied and that is very well understood, and in some kind of really fundamental work in geometric stability theory, which is the class of omega-stable, omega-categorical structures. But since I want to introduce as little model theory as possible, I'll define it slightly differently, and also because it will be useful for me later on. So I'll define those as ranked stable, omega-categorical. But if you know those things, this is just omega-stable. So let me define what I mean by ranked. And I won't define it. I won't give you a precise definition. So the definitions I will give are slightly wrong, but it will give you the intuition. So first let me tell you what it means to be rank 1. So I'll say that a definable set, so the rank is meant for definable sets in a structure. So a definable set has rank 1 if it's infinite, and there's no definable equivalence relation with infinitely many infinite classes on it. Yeah. So okay, so you cannot partition it in infinitely many infinite sets by an equivalence relation. And I'm lying a little bit, as I said. The real definition is you have also to ask that for finite covers of your set, but you don't need to worry about that. It won't come up. And then, so rank 1 means you cannot have an equivalence relation with infinitely many infinite classes. Rank 2 will mean, well, you can have one, but then each of the class themselves must have rank 1. But I'm mainly going to be interested in rank 1, so I won't even define the rank in general. I'll just say what it means to actually be ranked. Well, being ranked means that, and again, this is slightly vague, it means that you cannot find an equivalence relation with infinitely many classes, then on each class find another equivalence relation with infinitely many classes, and just keep going infinitely often. So you cannot have an infinite nested sequence of equivalence relation each with infinitely many infinite classes. By nested, I mean that each one, that for each class of one, you get a new one on the class, and you go on like this. So as I said, I'm lying a little bit. Usually you have to deal with finite covers. You have to be a little bit more precise. But this gives you, if you take this as a definition, it gives you a good enough intuition of what this means. I'll give you examples, but I should point out here, very importantly, that everything is defined with parameters. Because, of course, without parameters, you can define only finitely many equivalence relations, and so you cannot go very far. But if you have parameters, you can imagine that by looking at bigger and bigger sets of parameters, you'll be able to just define refining equivalence relations. Okay, so most of the basic structures that I showed you are rank 1. There's just no equivalence relation on them. Well, with infinitely, so of course the equality, FP vector spaces, you have one equivalence relation on being on the same line, but that has finite classes. You don't have an equivalence relation with infinitely many infinite classes. On Q, you just don't have any equivalence relation at all, non-trivial, even, yeah. So those have rank 1. However, very importantly, trees are not ranked. And let me show you why. So if you have a tree, you can take a point in it, and then every point defines an equivalence relation on the points above, which is what usually called open cones above the point. So you say that, so if you fix a point A, you can say that B and C are A equivalent, say. So it's an equivalence relation that has parameter A if the meet is above A. So if they're above A, so this is for B, C above A, and if their meet is above A. And okay, if you've never seen this before, you need to think a moment, but this is an equivalence relation, and it partitions, so it partitions the things above A in kind of cones. And the assumption of dense tree tells you that this has infinitely many classes. Right, but now each one of those cones is again a tree. So you can just keep going. You can again partition it and go on. In fact, in this case, you can even you even do it with the same formula every time, but just the parameter changes. So you just pick a point here and so on. So trees are not ranked, and that's going to be important, but it's also sort of the weakness of what I'll talk about, because I'll talk about results for ranked structures. Okay. So let me talk about the results on omega stable, or just ranked stable omega categorical structures. And there's a lot more than what I'm saying, and if I start going too much detail in the history, I'll probably say many wrong things. So let me just concentrate on the points that I'm interested in. So sort of the first step, which is again some fundamental step in the history of geometric stability theory, is Zilber, who classified primitive rank 1 omega. This is all omega categorical, is implicit, stable structures. So usually this is presented as just strictly minimal. So primitive here means the automorphism group acts primitively. It just means there's no zero definable equivalence relation whatsoever. And rank 1 I defined. And so the remarkable thing is that you can, so this says list. So you can give a complete list. You can say exactly what they are. They're countably many, and they're essentially pure sets and projective and affine spaces over finite fields. And there are some small prints, but essentially that's what they are. And yeah, so you can just give a complete list of those guys. I won't say exactly, so yeah, but essentially, so they're essentially pure sets and vector and some kind of things you obtain from vector spaces over finite fields. And And then the next step is, okay, once you understand the rank 1, you want to understand the general case. And there what you show, and here I'll be very imprecise, but there are kind of coordinatization theorem of Zilber. He did it in the totally categorical case, then Cherlin, Harrington, Lachlan in the general ranked stable case. And so coordinatization means that, well, if you have if you have a structure of rank 1, you know what it looks like, so primitive at least. And then say you have an arbitrary one, then you can find something of rank 1, and which is even 0 definable, and then over every point, maybe you can put a fiber, maybe it's a finite fiber, maybe it's an infinite fiber. If it's an infinite fiber, you can do it in such a way that it's again something of rank 1, and then you can go on like this. So you're building your structure by taking rank 1 sets and sort of so some kind of tree like that. But essentially, the point is that they're built out of rank 1 sets. So you understand the rank 1 set, then it's not the end. You still have to understand possibly how you build it. But so this is what coordinatization means. And of course, they prove more. They prove this smoothly approximable, which I won't go into. But one thing that follows, which was, I think, the initial goal of Zilber, is that those structures cannot be finitely axiomatized. And let's look for a moment, if you've never thought about this before, if you look at FP vector spaces, it looks like they can be finitely axiomatized, because an FP vector space is just saying it's an abelian group, every element has order P, that's finitely many axioms. But the problem is that doesn't axiomatize the structure, because this also has finite models. And if you want to actually have an axiomatization, you need to rule you need to say that the structure is infinite or has infinite dimension. And to say that, you need infinitely many formulas. But then the third point here is, so Albrecht Ziegler in a special case and Hrushovski in the general case proved that this is the only obstruction, that those structures are quasi-finitely axiomatizable. So it means roughly that you have finite axiomatizability if you allow yourself to say that certain things are infinite. So if you allow, say, to use the quantifier exists infinity, then you can. And the remarkable consequence of this is that there are only countably many such structures. Because once you have a finite axiomatization, you only have countably many. And one would need to say up to what? Up to interdefinability, you might have to change the language a little bit, but up to interdefinability, you only have countably many such ranked omega-categorical structures. And there's more work, notably on covers by Evans and Hrushovski, but that's not going to come up here. All right, so this is a beautiful, beautiful theory. And so the idea is maybe you can do similar things for finite dimensional. Maybe stable here is not so essential. Maybe you can relax it and go to NIP. It's really NIP. You can here finite dimensional for this ranked structures. You can think of it as NIP, but let me keep it like this. So we want to try to extend this picture. And okay, so we have 3 steps to do, and the difficult one, the main thing is to do the first step here. So the rank 1 structures, you just need to somehow be able to understand what they are. And so this we can do. So you can do the same thing. So you can give a complete list of the primitive rank 1 NIP of finite dimensional structures. And there are only countably many such. And the list is a little bit messy. But I'll try to tell you what's in it. So you have some. Sorry? Oh, primitive is just, it means first there's a unique 1 type, and there's no, and there's unique, it means there's unique one strong type. So it means there's a unique one type and there's no zero definable equivalence relation. So that's just to rule, otherwise, yeah, I mean, so if you have a zero definable equivalence relation, you quotient out by it, and then it becomes primitive. So, okay, so what are the primitive? So first you have the stable ones, and this I just take as a black box. So the stable ones, I'm not reclassifying them. You just take the theory as a black box. And then it so happens that if you're not stable, then you have to be really not stable. You have to be distal, and there's nothing stable that's going to come up anymore. But contrary to the stable, so okay, so let me give you some kind of so let me give you a list of structures that are in it. So of course you have dense linear, so the unstable ones. You have Q with the order. That is rank 1, finite dimensional. You have the circular order. The circular order. That's also rank 1 finite dimensional. And if you know those things, they each have a reduct where you add an automorphism of degree 2 that switches it. I'm not going to write it. And that's not, I would like to say that that's it, but it's not completely. You have also some structures that are expansions. So the dense linear order does not have any expansion that is rank 1 primitive. There's nothing you can add to it. But the circular order, you can expand it a little bit. And I mean, sorry to go in those details. So you can, this is a well-known structure also. What you can add to it is, you can add some kind of directed graph that to every point just goes to an initial segment of the circle starting at that point. And you can do that. So the simplest way to do that is okay, so you take the circle and you map to the initial segment of length 1 over n starting at that point. And so for each value of n, you get a new structure that has this kind of directed graph thing. So okay, they just come up. So it essentially allows you to say that 2 points are at distance less than 1 over n on the thing. Sorry? So you can, this actually becomes a binary structure. You can just, you add, for example, this directed graph, or you add, I mean, there are many ways you could expand it to have. So this, you can think of it as adding some relation that says whether 2 points are close or at distance less than 1 over n on the circle. And you need to think a moment why this doesn't really exist. You can't do this in a linear. It's really important that you have a circle here. Otherwise, you would lose omega-categoricity. And that's it. So, no, sorry, that's not it. That's it for the ones that have linear growth. So that's it for the linear growth for S of A is big O of A. But then, contrary to the stable case, you also have things that have, in some sense, higher dimension. So what you can do also is you can take a structure and put 2 linear orders on it. And you can take the Freise limit of this, of a thing with 2 linear orders, which means you just get 2 independent linear orders. So they have no, so any interval for one of the order is dense, codense with respect to the other order. And this looks like this is essentially a 2-dimensional structure, but it still has rank 1, which is sort of the annoying thing that happens when we leave stable. This should be a 2-dimensional structure, but there's no equivalence relation. You can't define any equivalence relation on it. So it still has rank 1. So we still have to list it. And then you can, of course, you can put a linear order and a circular order, just independent. And then things start to get a little bit messy. If you have 2 linear orders, they could interact in a certain way. But I don't know how much you want to know about that. But essentially, you can take 2 linear orders. I won't be long. And you can well, you can take two linear orders, but that are sort of that fit into a bigger order. So they each dense codense into each other, and you can put an edge randomly between a point on one of them and a point to the right on the other, and so have some kind of pairing where every point on one is linked to another and quotient out by that. And that gives you a structure that has two linear orders. You have to think about it, but that are not completely random, but almost. And you have things like that that appear, and you can do similar things with circular orders, and it's a little bit. And then you can have more than two orders. But essentially, that's almost as complicated as it gets, this kind of thing. So it's only things that you get from taking finitely many linear orders and maybe some edge relations and quotienting out, and plus this kind of structure. OK. So I think I have a small observation, is that in particular we get this, we get the redux of the LO from this. We can read them out. It's a known theorem that the redux of the LO there are only 4 or 5 of them, and this gives some kind of model theoretic proof of it, because the redux of the LO has to be rank 1 primitive. And it would be interesting to know if one can do a similar thing for the random graph, for example. OK. So this is kind of the application of the result I really want to talk about. And so a year ago, this would have seemed quite out of reach, because we had no idea where to start. We had no idea what to do if you have an NIP omega-categorical structure. And so the main theorem that makes it work is that we can find linear orders. So this is sort of the main theorem of the talk in some sense, or a special case of it. So if you take an NIP unstable omega-categorical structure, so if you don't want to think about NIP, you can find dimensional, then it interprets an infinite linear order. So interprets means maybe you don't have a definable order on the structure itself. Maybe you need to pass to a quotient to find the order, but you can find one. And so this tells you really that this polynomial growth will only come from, either stable things or linear orders. And I don't think I'll have time to say anything about the proof of this, but there's not much you learn from it. It's really playing around with NIP. But of course, you don't just find one order. You find orders everywhere you want. Everywhere that's not stable, you can find an order, a linear order. Let me tell you a little bit about how you go from what you need to go from here to here. So this just tells you that you have your structure M, and this tells you let's forget about the quotient. If it's rank 1, there's not going to be much quotienting going on anyway. So let's say you have your rank 1 structure, and this tells you somewhere you can find a linear order, definable with parameters. That's the problem. So somewhere you can find a linear order. Maybe it doesn't cover the whole structure, so you just have one here. But since your structure is primitive, there's only one type, so you have linear orders everywhere. So your structure looks like this. And then you have to understand how two linear orders can intersect. And what you notice is if you have two linear orders that are definable, that start by agreeing and then change their mind and then go in different directions, then from this you can build a tree. And since you're assuming rank 1, you cannot have trees. So then you realize that linear orders can only sort of go together like this. And so what you do is you take one and you extend it as much as possible, and then two things happen. Either it comes back to itself and you get a circular order, or it doesn't and you get a full linear order. And that's sort of the proof in the linear case, and then otherwise you have to deal with more than one order. And it's slightly more annoying. But essentially, once you have that, the proof is a lot of playing around with just looking at what could possibly happen. And there's no big idea. There's no new big idea involved. All right. what else do I have? Okay, so where to go from there? So you should be able, one should be able to do the next two steps. So it should be true that finite dimensional rank structures can be coordinatized by rank 1 sets, and that they are quasi-finitely axiomatizable, and I add finitely axiomatizable if and only if they're distal. That's not a big deal. But the point here is that this is a very different status of conjecture as the first one. This, I think, you should actually be able to do it just by doing this, just by adapting the known arguments.
What was the first one?
The first one was the conjecture hope that you could classify. So this should be well within reach because, and I some ideas of how to do it. The thing is, once you know the rank 1 set, the rest of the theory does not use stability very much. So it mainly uses the properties of the rank 1 set. And so the fact that our rank 1 sets here are quite simple when we have the stable ones, and then we have only linear orders, which are sort of geometrically trivial. For the first guy, I'm almost sure. The second one, you need to maybe adapt. You need to make a little bit more effort probably to adapt the arguments. But essentially the same arguments as in the stable case should go through and give you those two things. All right. So this is for the ranked case. Now I do have time to give you some precise conjectures in the general case. So as I said, I don't actually have precise conjectures for finite dimensional omega categorical. In particular, there are continuum many such structures, so you can't expect too much. However, if you restrict in a different direction, if you restrict to finitely homogeneous, then one can hope that things work well. So let me make a conjecture. So let's look at finitely homogeneous. Here I say NIP, finite dimensional is the same thing once you've said finitely homogeneous. So let n be finitely homogeneous. I'll make two conjectures. First, that the automorphism group acts oligomorphically on the space of types. So in particular, there are finitely many types of the automorphism, but this is saying a little bit more than that. And the second, so you need, maybe if you've never seen this again, you need to think why it's true in dense linear orders, for example. Or maybe I can say it. So in dense linear orders, if you look at the space of types, you have, so what types do you have? You have one type at minus infinity, that's invariant under the automorphism group. You have one type at plus infinity. Then you have types that are realized types. Those form one orbit. Then you have the type that goes just above a realized type. Those also form one orbit. You have the type that goes just below. And then finally you have one more type which goes into a Dedekind cut. And those also form one orbit. So you have this many, 1, 2, 3, 4, 6. You have 6 orbits of one types in dense linear orders. And okay, I conjecture this is always true in finitely homogeneous NIP. And they should also be quasi-finitely axiomatizable, and finitely axiomatizable if and only if distal. So I didn't define distal in this talk. It's not so important, but if you know what it means. So things like, but well, here distal should really mean that there's no stable set definable in it. It should be equivalent. And then you get finite axiomatizability. And I should point out that actually one direction of that is a fun exercise. So if you have a finitely homogeneous distal structure, then it's finitely axiomatizable. And this doesn't require any structure theorem. You can just prove it directly from the definition. And it's a fun exercise to do. If you know what distal means. And this is a question I thought about really while preparing this talk, so I haven't thought about it at all. But this sort of gives you an oligomorphic action on a Kantor space. And I just was wondering whether those things were, whether there were many such things or not. So maybe this is a silly question, but maybe someone would know the answer to that. So that's why I wrote it here. I was just wondering, yeah, so I don't know. Okay, do I have anything more? No, okay. So I'm done with the omega-categorical case. So there are many conjectures. And yeah, I should say, how can one hope to prove such a thing? What is the problem with trying to adapt those arguments? First, here we don't have any rank, so we don't know where to start. And we have to deal with trees. This is the main problem. One has to understand. So you can prove that if you're not ranked, if you're finitely homogeneous not ranked, then you're certainly going to have trees definable. And then you somehow have to deal with them. And trees are complicated. So this is really what is missing to approach this problem, is find a way to handle trees. Okay. All right, so now let me leave combinatorics and just tell you what's the results about the general NIP case. So yeah, I should say that there's a conjecture that has been around for like over 10 years, and which received some attention at the time, which was, if you have an unstable NIP structure, does it interpret an infinite linear order? Because essentially the only unstable NIP structures we know are things like real closed field or valued fields, and they all have linear orders. In the real closed field, you have it already. In the valued field, you have a tree that's definable, and you get linear orders. Scheller proved that in the 70s, at the very beginning of all this, that if you have an unstable NIP structure, then you have a definable partial order with infinite chains. And the whole question is, can you go from a partial order to a linear order? And so I don't, this is still open, I don't know that, but I know something which is quite close. I can't get definability, but I can get type definability. So if you have a NIP unstable structure, then there's some finite set and a relation which is type definable over A, which gives you a strict quasi-order. So quasi-order just means if you quotient out, you get a linear order. So maybe you have elements that are not comparable, but this is an equivalence relation if you quotient it out. And if you think about this, this will give you the strict order. So the relation of being incomparable is going to be V definable. So what you get is you get a V definable quotient, a V definable equivalence relation, and on it you have a linear order. And so you can see this implies immediately the omega-categorical case, because in omega-categorical, type definable is just the same thing as definable. So everything becomes definable. I can tell you why. Actually, it's reasonable to get this and to not get. So I don't know if one can upgrade this to having a definable linear order, but it's very reasonable that one would actually get such a statement. I mean, the methods used are not going to give you more, or never going to give you more than that. You'll have to find some use. It's tempting to try some compactness argument to get this definable. I didn't manage. Maybe it's possible. But if you take this a very easy structure that's not omega-categorical, if you just take Z with the order, but take a saturated, so a saturated model of that will just be a linear order, which is discrete. And then inside a class of points at finite distance, all the points are interdefinable with each other. It's going to be very hard to distinguish one point from another by kind of methods using indiscernible sequences and all of that. So what this theorem would give you in this structure is the V definable equivalence relation will be those classes. And then each class, and then if you quotient out, so you see this is V definable. It's a countable set. It's a V definable set, and of course the classes are themselves ordered. So this is in the case of Z with the order, this is what the theorem will see. It will see the quotient. And once you have the quotient, trying to see the actual order, this I don't know how to do. But this might be good enough. And even there are some reasons why sometimes it's actually better to have a V definable, because then you get some things for free by compactness somehow. And so for me, this actually, it seems like a technical, I mean, it is just a technical result, but for me, it rather changes the landscape of NIP, because it makes it possible. It says that NIP structure are much more structured than we thought. You can actually find linear orders everywhere, and things are controlled by those linear orders in a sense that I don't exactly completely understand, but it really makes it plausible that one could develop a classification theory for subclasses of NIP, maybe finite DP rank, something like that, similar to the one for superstable, where you will coordinatize things by linear orders. Because you can find a lot of them, and it's very tempting to try to reconstruct the structures from them. But this is, well, the main thing that, I think the main thing that sort of blocks me at the moment is that you need to understand the induced structure on those orders that you get. And I mean, the idea is those orders should sort of play the role that regular types play in superstable. And in regular types, you understand the structure you get is a pre-geometry. And then you have dimension and this. Here you get linear orders, and you'd be very happy if those linear orders were just pure linear orders. And in many cases, they actually, well, actually in all cases that I've looked at, they actually are. And if they are pure linear orders, if somehow one can prove this, then you would immediately, you would be able to build models at least. For example, building 2 to the IF0 countable models or things like that would be, would follow at once if you can understand the structure on those, on the orders that you get here. And so, but this I don't know how to do. Is there anything more I want to say? I can say a few words about the proof, about how you find this order, just in 2 minutes. So this is a little. So Sherlin's, it starts with Sherlin's idea of how you get a partial order. So if you have an NIP structure, there's some indiscernible sequence. If it's unstable, there's some indiscernible sequence and a formula which is false on a big set of the sequence and true on the other part of the sequence. And this is what Sherlin starts with to build a partial order. And you can choose the formula and the sequence such that if you vary the parameter A, the formula is still going to be false then true, and nothing else is going to happen. It's not going to be false, true, then false. So whenever for any parameter A. So now what you want to do is you want to open up, so sorry if it's a bit technical moment, you want to open up the sequence here, and if you put in a new, if you increase the sequence in the middle, then this formula is still going to be false on an initial segment and true, it's going to cut this middle piece that you put in. But now if you vary A, you will get different cuts. If you instead of A, you take phi of xi prime, phi of xi prime is also going to be false then true, and it's going to change its mind in the intermediate piece at maybe another point. And now you want to order A and A prime depending on where they change their mind. But now, so this always gives you some kind of partial order, then that's Sherlin's proof. But now you want to make it linear. And for this, you work a little bit more. So essentially, you show that if it wasn't linear, it would mean that you could put in a piece where it would mean that you could put in 2 pieces where they change their minds in opposite directions. So for one piece, A changes its mind before A prime, and for another, A prime changes its mind before A. And you show that if you can do this too much, then you contradict NIP, because you'll be able to switch, you'll get n points such that you'll be able to switch the relative orders of their cuts arbitrarily. So you have to work a little bit. But just to give you some idea of what's behind. It's like playing around with indiscernible sequences and NIP. And this also shows you that you get those linear orders as soon as you have such a situation, an indiscernible sequence and a formula that is true. So you get lots of them, and that's quite useful. All right, that's it. Yes.
Yep. Regarding the hope of classifying using linear order, how do you deal with the fact that you could have very small orderings? There is no notion of like a maximum linear ordering. So you could have only typedefinable orders everywhere. But
Yeah. So, I mean, the short answer is I don't know. But of course, so the idea is you would fix a small model. You would look at all the ones that are definable there. And it's like in stable. In stable also, you might have regular types that keep showing up. So here, yes, you might have new orders that keep showing up. So you'll have to deal, so there should be first a sort of one-dimensional case, like RCF. Even RCF, it's not completely clear how it would work, but you could like look at the type at plus infinity, look at the order that you get sort of from this construction using it, and I think this, I haven't thought too much, but I think this should give you some kind of already. So yeah, of course, you might have new orders that keep showing up as you take bigger and bigger models, and it's like in the stable case, maybe you can deal with them, or maybe just assume they don't exist, or I don't know. I mean, yeah.
So you said something about expecting these linear orders to be pure, but if you look at RCF, don't you get a value group?
Yeah, that's what I thought, but actually you don't, because those linear orders are bigger than the valuation ring. They see the whole field structure. So you're going to quotient out by, not just by sort of what you would if you had a valuation, you're going to quotient out by powers. You're not going to quotient out Archimedean classes. You're going to quotient out Archimedean classes for the product, and then I don't think there's anything left. It's possible that I had the impression that it worked.
So in the omega-categorical context, the rank 1 is used to say that the order you get is pure, or because your NIP theorem already gives you the order.
Yeah, well, yes, and you need to patch them together. I mean, you get a linear order on some part, but yes, otherwise it's a fun exercise, for example, to prove that this has no expansion of linear growth. That's also when DP rank 1, if you want, that's omega category. Yeah, so it's useful, those two things. Yeah.
Yeah. So you said you also recover Kamaran's theorem, right, for the typedefinable freedoms?
Yeah, I think so. I guess you have to rule out those. So, but
so you have, I mean, it's a very important part of the proof is using Ramsey's theorem. So do you use this in any explicit place or only in the indiscernibles part?
no, you don't use this at all. It's sort of used in the constructing the order. But if you take this construction of the order as a black box, then it's never used.